Today is the first lecture on continuity. We already had one very informal class on continuity, but let us not count that. So, in the last day, we had seen this quote by mathematician Sylvester. Geometry formerly was the chief borrower from arithmetic and algebra, but it has since repaid its obligations with abundant usury. And if I were asked to name in one word the pole star round which the mathematical firmament revolves, the central idea which pervades the whole corpus of mathematical doctrine, I should point to continuity as contained in our notions of space and say, it is this, it is this. Now, to explain why we need to study continuity is a philosopher's task, and we do not intend to do that here today. As an infant, when you were first taught about counting numbers, there were not much of a motivation given to you that why you need to learn the counting numbers. But as you grew up, you realized the omnipresence of the counting numbers around you. Study of continuity is as organic to analysis as counting numbers are now for your life. And it's only after learning you realize its presence. Hopefully, then we will be able to appropriately appreciate the quote after this learning process, after we learn continuity. Okay? Informally speaking, a function is continuous if its graph can be drawn without picking up the pen from the paper. Now we want to describe this phenomenon mathematically. To get the definition of continuity, we want to describe this phenomenon mathematically. We often do that with a contrary statement. Okay, contrary situation. A function is not continuous if you cannot draw the entire graph without picking up the pen from the paper. In other words, the graph has breaks in between, just like this one. This graph has breaks over here. Now, to formalize breaks in a graph, a good way to describe it is through the concept of neighborhoods, neighborhood of a point. The point on the graph where the break occurs should have a neighborhood not containing any part of the remaining graph. Look at the scenario here. This is the point where the breaking is occurring. Now, if at this point, this is your FC, and this is your neighborhood FC plus epsilon to FC minus epsilon. This one does not have a portion of the graph contained over here. This neighborhood does not have a portion contained over here. On the contrary, for a continuous function, every neighborhood of a point on a continuous graph should contain some part of the graph, like this. Any point on the graph of a continuous function, every neighborhood of that point, this is my point, I am considering the neighborhood over here. So this is my neighborhood FC minus epsilon to FC plus epsilon. This neighborhood contains graph of the function in both sides. So for every epsilon positive, epsilon neighborhood of a point fx on the graph should contain some part of the graph. That is, it must correspond to some delta neighborhood of the independent variable x, such that the entire graph of the function from the delta neighborhood of x lies completely within that epsilon neighborhood of fx. Okay, the epsilon neighborhood contains a part of the graph, means that neighborhood will correspond to some neighborhood of this point C, so that the entire portion of the graph from this neighborhood of C minus delta to C plus delta, that entire portion of the graph must be within this epsilon band of the point FC. On the other hand, if a function is discontinuous at a certain point, like over here, at a certain point C, then FC will have a neighborhood along the graph, okay, will have a neighborhood along the graph, so that no corresponding neighborhood of X can push the entire graph into the neighborhood of FC. You see here, for this choice of delta, for this delta neighborhood, this portion of the graph is staying outside of the epsilon neighborhood of FC. For this choice of delta, still this much portion of the graph is lying outside of this choice or of this neighborhood of FC. Even for this small delta, the neighborhood, the graph is staying outside of the epsilon neighborhood of FC. So motivated from here, this scenario, we set the definition of continuity as a function from R to R is said to be continuous at a point C if for all epsilon greater than 0, there exists a delta positive such that mod of x minus c less than delta implies mod of fx minus fc is less than epsilon. Okay, for every neighborhood, for every epsilon neighborhood of fc, you can find the delta such that whenever x is coming from the delta neighborhood of c, fx must come from the epsilon neighborhood of fc. Okay, do you see how this definition is coming from the light of the discussion we had over here? For every epsilon, so for every epsilon positive, for any neighborhood over here, in this case, you can have a delta for any neighborhood, for any band around this point FC, you can find a neighborhood of this point C, so that the graph of the entire portion within C minus delta to C plus delta will be within this portion, FC minus epsilon to FC plus epsilon. Okay, so this one I am characterizing in this definition that for all epsilon positive, we will find a delta such that x is coming from the delta neighborhood of C implies fx is within the epsilon within epsilon distance of fc. Now paraphrasing this one, we said the continuity on a domain. We chose over complete R over here. We set the continuity on a domain. Let D be a non-empty subset of R. A function f from D to R is said to be continuous at a point C in D if for all epsilon positive, there exists a delta positive such that for all x in delta neighborhood of C intersection D, we will have fx minus fc, the mod value will be less than epsilon. That is, fx is fx will fall in the epsilon neighborhood of fc. Now, f is said to be continuous over D if it is continuous at every point over D. This is the definition over continuity over a domain, entire domain. F is said to be continuous over D if it is continuous at every point C in D. Now, at this point, can you tell me what is the basic difference of this definition you are looking at from the definition of limit of a function? Exactly, deleted neighborhood. The point in concern in limit did not have to be a part of the domain, or we actually did not want that to be part of the domain, right? But when we are doing continuity, continuity must be on at a point inside the domain. Second, the difference what is there? What was C in the case of the definition of limit? Limit point, exactly. That is not needed here. If I, in this definition, I also assume that C is a limit point of the domain, then what does this statement say? This will mean that limit extends to C of fx is equal to fc. So in your school, where you learned the definition of continuity as function is continuous at a point C if limit of x tends to C of fx is equal to fc, that definition is sort of a derived definition, not a very general one. For future references, let us also record the definition of discontinuity at a point. D be a domain a non-empty subset of R, a function is discontinuous at a point C if, tell me, for all epsilon a positive, something happens. That negation means there exists a violatory epsilon for which something does not happen. Next, there exists delta such that something happens. So negating that for all delta, something does not happen. Next, for all x in this point, something happens. Negating that there exists a violatory violatory x delta, point x delta, such that something does not happen. Now something is the last part. So fx minus fc is less than epsilon. So fx delta minus fc will be greater than or equal to epsilon. That's it. You break this in every part, and then you negate. For all becomes there exists becomes for all.